Yeah, maybe we should begin. Hi everyone, I'm Jin-Peng. Currently, I'm a Simon's Quantum Postdoc Fellow at Simons Institute and US Berkeley, and joint host by Umes and Lin. I will be a postdoc associate at the Center for Theoretical Physics at MIT. Today, I would like to talk about quantum scientific computation. As we know, and we just know, introduced by Dee, and the quantum computers can make use of some quantum mechanical phenomena such as superposition or entanglement to perform certain computation. So these pictures show some currently near-term quantum device built by some famous companies such as IBM, Google, and also other research groups. And why we are concerned with quantum computers? Because they can significantly outperform classical computers for certain computational problems. And I would say, and currently there are tremendous numbers of work focusing on quantum computers for solving linear dynamics and discrete models, such as the Hamiltonian simulations, which has been covered by this talk. And also another large class of problems based on the quantum algorithms for solving systems of linear equations. That I would like to start by these algorithms. And so this is basic problem model. So the so-called quantum linear system problem. So considering that we have some certain description of a certain S-sparse n by n linear system as shown in equation 1. So where we should assume the sparsity S, that means a parameter that upper bounds the number of non-zero entries in each column and each rows in the measure A is significantly smaller than the dimension n. So for such a kind of sparse linear systems, and we aim to efficiently solve the problem under some complexity that is extremely smaller than the classical linear system solvers. So for that problems, so quantum computers is able to produce a quantum encoding of such an inverse solution, and with such a complexity, which has a linear scaling in terms of the sparsity S, linear scaling in terms of the condition number kappa, and has a polylogarithm dependence in terms of the dimensionality n, which has a exponential speed up in terms of the dimension and compared to the classical linear system solvers. Here, I would like to emphasize that it's no hope to produce all the entries of the vectors X, and because you will take at least linear n. However, and maybe there's a hope that under some measurements, it's possible to take some problem measurement to answer certain questions faster than classical algorithms. Yeah, so and after we discussed the quantum linear system solvers, now we are focusing on more complicated realistic problems and the so-called scientific computation problems. There are some pretty famous models for problems, such as the modeling the climate changes and the model the spread of epidemics and how to model the derivatives of price. So for such problems, the basic, or we can say the crucial challenges in terms of the design of quantum algorithm is the gap between the linearity of quantum mechanics to the real-world systems with many-body, nonlinear, as well as stochastic interactions. So my research based on basically speaking, my research aims to address these three types of the different difficulties, but today I would like to just focus on the nonlinear ones. So why nonlinearity is extremely difficult in quantum computing, even harder than classical computing? Basically speaking, and it can be based to the so-called quantum no-calling theory in the quantum mechanics. But here I would like to mainly cover the difficulty in two aspects. For the algorithm side, and the previous algorithm, I would say before the 2020, and the previous quantum algorithms for solving general nonlinear differential equations must take exponential time and space complexity for that problems. And on the other side, we have some lower bound results on addressing these problems. And actually, people have shown that nonlinearities can imply polynomial time solutions for NP, complete, and even for Sharpe problems. And for particular case of nonlinear Schrödinger equations, one can show for if there has some strongly nonlinearities and strong nonlinearities, and the quantum algorithms must have a worst case time complexity exponential in T. So this is the reason that why people think the nonlinearity is difficult, and actually it was a long-standing open problem in the field of quantum computing until we try to tackle it. So for that problems, and our contribution is that we developed the first efficient, I mean efficient means polynomial time, quantum algorithm for weakly dissipated nonlinear differential equations. We also give at an almost tight lower bound result, showing that only nonlinear ones are generally intractable. So this paper was published in PNAS, and also we have been this result has been covered by the Quanta and other media. And so now we can look at the problem models. We are interested in addressing such kinds of the quantum nonlinear ODE problems. So I'm showing in the equation 2. So, and for such a kinds of the system of the n-dimensional quadratic ODE systems, and here and F2, F1, and F0 are the matrices or vectors to represent the quadratic couplings, linear couplings, and the linear inhomogeneities. And we aim to simulate the system starting from initial state to a final state. And we further assume this system should be, we assume is dissipated. That means the real parts of the eigenvalues of F1 should be negative. And for instance, for the so-called Borders equation, which is kind of one-dimensional Navier-Stokes equation, satisfies such a condition under some proper boundary conditions. And given such a very general problem model, and we define important parameter R, as shown in here, and it's used to quantify the nonlinearity strain related to the linear dissipation. That means if R is small, that means the linear dissipation dominates the nonlinearities and other terms. So we say a small R represents a weakly nonlinear system. So if R is small, maybe it's possible to solve the problem. So yeah, that is then. So we consider such a framework, and we consider how to perform a proper linearization for targeting these problems. And regarding linearization, maybe we will think about some naive linearization based on the linear Jacobian matrix. And we could imagine like this toy model. So if we replace U squared by U0 times U, and then this linearization cannot work in a long time. And so we need to seek for some long time and stable linearization method. So we pick up the old school technique, so-called Kalman linearization. Here is the base framework. So first of all, we can embed an n-dimensional nonlinear system into an infinity dimensional linear systems. And secondly, for the algorithm side, we must truncate the system to go back to a finite dimensional system. And actually, the key is that we need to preserve the dimensionality to be at the most polynomial in terms of n. And for such a truncation, we can prove the truncation error converge under the condition R is smaller than 1. So the previous parameter R can be understood as a certain convergence radius. So, and given such a linearized system, we have introduced the so-called quantum linear system algorithm, so for which we can perform proper discretization and perform the quantum linear system solvers to solve the problem to provide a quantum encoding of a solution with a compressive polylogarithm in terms of n. That is the base framework. So here is the basic statement of our main theorem. Given the condition R is smaller than 1, there is a quantum algorithm to efficiently produce such a quantum state corresponding to the solution. And here I would like to emphasize that the math contribution, that means independent of quantum computing, we improve the previous best known convergence analysis of Kalman linearization. And our state-of-the-art analysis has been applied to classical nonlinear control series and classical CFD, which is all independent of quantum problems. And on the other side, why I say it's almost tight result, because on the other side, we also give a lower bound result under the condition when R is larger than or equal to square root of 2. That means we only leave a very narrow gap between 1 and square root of 2. So this is basic result. And we show instance of such a problem, such that any quantum algorithm must have worst case time complexity exponential in T. So the proof strategy is as follows. First of all, we know some basic lower bound results in the quantum information theory, such as we use the hardness of distinguishing two orthogonal, non-orthogonal quantum states. And secondly, there is a well-known effect, the so-called butterfly effect. Variously is the so-called initial sensitivity. That means if we are given two possibilities of initial states with a very small difference, after very short evolution time, the small difference will result in a large variation, like this picture, and one solution goes up and the other and goes down. That means we will fastly change the states of this, change the two states and under the same evolution. So given such a capability, and so if there exists a quantum algorithm that can efficiently simulate such a chaotic system, that means it provides an efficient way to efficiently distinguish non-orthogonal quantum states, which is believed to be impossible. So based on such a result, we show the worst case time complexity exponential in T for arbitrary quantum algorithms for such example. Finally, I would like to briefly cover the applications of series and algorithm in recent years, and so the first application is for fluid and plasma dynamics, and because we can only target for weightedly nonlinear differential equations, so actually numerical result and some a little bit theoretical result can show that our linearization works for low nano number flows, the so-called laminar flows, and maybe we cannot target for turbulence. So, and based on some recent results, I was invited to give a semi-plenary talk at the annual meeting of the APS division of fluid dynamics and last year. And the second application is for the control theory, like it can be used to find certain attractors or study the reachability problems. Thirdly, and we also study how to apply the linearization algorithm for the certain SER model, which is well known for modeling the spread of epidemics, and we study under the so-called rapid vaccination condition, and our algorithm works for the realistic parameters in the world. And finally, and we also study the applications in economy and ecologies, and we can use this algorithm to solve some certain nonlinear PDEs, and which is used to model like predictor prey cycles or economy models and for the realistic world. And this is a final page maybe, and here during my talk I would like to cover only cover the breakthrough and for the nonlinear dynamics, and it's connected to many types of applications, regardless of the applications for OD and PDEs. It can also be used to study networks, particularly for epidemics problems. It can be used to study the gradient flows for optimization or machine learning problems. It can be used to solve some equations showing in the optimal control or reinforcement learning. My research also covers other types of the studies, like how to simulate many-body systems, including classical and quantum many-body systems, from the quantum dynamics to the molecular dynamics. And lastly, I also try to study some polynomial quantum speedups for some stochastic process, like how to design quantum algorithms for speedup, like Langemann Monte Carlo methods or general MCMC algorithms, or how to use this algorithm for option pricing or for decision-making algorithms. And yeah, that's it. Thank you.
Thank you very much. Any questions?
When you say quantum ODE, what are the difference between standard ODE and quantum?
Yeah.
Can you repeat the question?
Yeah, sure. And so the question is that what's the difference between the classical and quantum nonlinear ODE problems as shown in these slides? And basically speaking, first of all, and given a certain equations, and the initial state is a quantum encoding of the initial value, or just say the data set. I mean, we need to have some procedure to upload the data into construct or to the quantum computer. So we have a quantum encoding of an initial condition. Then the output is also a quantum encoding of the final state. I mean, we try to produce a quantum state and the corresponding, maybe I shown in here, quantum state and the UT and stored in a quantum computer, which is corresponding to the classical state. So as we introduced at the beginning, so there's no hope to produce all the entries of these high dimensional vectors, but we need to perform some certain measurements to properly take some projections of the vectors to answer some certain questions.
Okay. Thanks. Yeah, maybe we can take the remaining questions over the coffee break. So thanks to all the speakers of the session. We break now for half an hour, and then we'll come back 3:30 to finish off the talks for the day. Thanks, everyone.